When a geologist looks at a picture like this one, they see an entire story laid out in front of them. What we hope to do today is learn to think like geologists, that rocks are actually telling us a story if we only know how to read that story and interpret it. So you've probably learned before about the rock cycle, and this diagram overviews that rock cycle, and I expect that you probably know it pretty well, that when rocks get hot enough, they melt down to become liquid, and if it's inside the earth, we call that magma. And if that magma were to cool down, it would crystallize into mineral crystals, and it would form a solid igneous rock, and that would be a volcanic rock. Now, those igneous rocks don't necessarily stay igneous rocks forever. They can have lots of different things happen to them. Well, one possibility is that it could always be melted down again and become magma again and go through the cycle and become an igneous rock again. And we see that that certainly is a possibility illustrated on this flowchart. But you also see how it could just go through the regular process of weathering and erosion and deposition as sediments. Those sediments can get compacted and cemented together, and now you have a different type of rock, a different rock family, as we might call it, and that is a sedimentary rock. Those sedimentary rocks may not stay as sedimentary rocks forever. As you can see, there are different possibilities. It could go and get heated up and become melted and go to become an igneous rock again. It could weather and erode and deposit and become a different sedimentary rock. Or another possibility is get it subjected to heat and pressure to become a metamorphic rock. And as the name implies, metamorphic rock means one that goes through change. So the change for metamorphic rocks is going to be something that would be adequate amount of heat and pressure, but not so much heat that you melt it, because if it did, that would be something that would form magma and then an igneous rock. But the pressure that we're talking about isn't just like the weight of rocks on top of it. I mean, that can play a role, but usually we're talking about the type of pressure that's associated with plate tectonic movements. So all of these different things can happen to rocks to cause them to change around. And the big message is that rocks will change over time. It's just that they change on a time scale that's much slower than what humans are used to. So we talk about geologic time scale being the time where rocks go through change. So what we hope to do here is help you to identify characteristics that are important for these different rock families. So the three different rock families we just mentioned are igneous, metamorphic, and sedimentary. And I want to try to talk about the key ideas of what you should look for. Now, when you think about igneous rocks, think about what we learned with volcanoes, that volcanoes aren't all the same. They're from igneous means from fire, and if you think of the word ignite, that helps you to understand what we're talking about. You should know that igneous rocks don't all look the same. They're going to look different based upon, first of all, their chemical composition, because you'll have different elements and compounds present. They'll also look different based upon their crystal size. And finally, something that helps distinguish certain ones are the presence of gas bubbles. So first, chemical composition. Remember that not every place that has a volcano formed in the same way, and they are different depending upon the temperature. Recall that the higher temperatures that you get in a hot spot and a diverging plate boundary, those tend to cause lower percentages of silica, higher percentages of iron and magnesium, because remember, they had a high melting point. So they're able to melt when you get those high temperatures. That reduces the amount of silica. That changes the chemical composition. So what do you get? You get something called mafic rocks. Mafic rocks are going to be, well, first, the word comes from the fact that the Ma stands for magnesium, fic from the word for Latin ferric, is associated with iron. Mafic rocks, you can pick them out because they will tend to have a darker color. They will tend to be more dense. And so here's a picture of an igneous rock that is mafic in composition. Something that has more iron and magnesium tends to have that darker color, will have a greater density. Now, compare that to what we get at a subduction zone volcano. They will tend to have lower melting temperatures, so that means that you're going to have a greater percentage of silica. Iron and magnesium stay solid, doesn't melt into the magma, and as a result, you end up with a lighter color with this rock, and it's going to be called felsic. The name felsic is going to be represented the fact that it's feldspar as the main mineral, which is a mineral that's high in potassium or sodium, and sic comes from the word silica, which is going to be in high abundance in one of these particular rocks. So felsic rocks, lighter color, and they're going to have less density than a mafic rock. Now, another thing that's important is crystal size, that the size of the crystals that you get in the rock will depend on the rate at which it cools. So if you think about magma, it's underground. So that means it cools slowly. And if it cools slowly, that means there's more time for the random kinetic energy of the atoms to move themselves into a repeating pattern before it actually crystallizes and solidifies. So the size of the crystals can be larger when your cooling rate is slower. That's why if it cools underground, it will result in larger crystal sizes. If it comes to the surface as lava, the cooling rate is much faster. The size of the crystals are much, much smaller. And when we're talking about large crystals, really something to keep in mind is large means like you can easily see it as distinct crystals with the unaided eye. Small crystals, sometimes if you really look close, you can tell with the unaided eye that it's got separate crystals, but sometimes you need magnification to see it. And if you had really fast cooling, then you get zero crystals. It just forms this glassy surface, and that's something that's pretty unique and stands out. So you can look for that. That is a sign of very fast cooling. The last thing to look for is some of the rock samples will show gas bubbles. And what we find is that if you get lava that's close to the surface, it has less pressure on it. So that means that the gases that were dissolved in the liquid will tend to escape. They're tending to push out of that liquid. However, it's cooling so quickly that they don't get to fully escape necessarily. So you get them trapping those gas bubbles and kind of freezing them in place. So you can kind of think of this as the foamy surface of a lava flow. And when it cools down, it's cooling down fast, so it's trapping those gas bubbles and it solidifies them into place. That's a characteristic of some volcanic rocks that are bubbling to the surface and cooling very rapidly. Okay, so sedimentary rocks, what do we look for? Well, because we know that sedimentary rocks form by weathering first and then eroding and depositing in a certain location, they then get compacted and cemented together. One of the things we want to look at is their grain size, which basically means the particle size of the things that go into making up the rock. Another thing that we'll look for is the presence of fossils, because that could be a big clue about what the method was for forming this rock. So as far as grain size goes, we know that we actually didn't do glaciers very much this year, but when we looked at other issues with sediments, when they're carried and they are dropped, it has to happen where the eroding agent, the water that's carrying it, has to be moving with enough energy to be able to pick up that particle size. And so what typically happens is a river might be moving fast and picking up big particles, but then when it slows down a little bit, the type of rock that's going to drop are going to be the biggest ones first. And so that would mean that your agent of erosion, the water, was moving very quickly if you have big particle sizes all grouped together. Now, what we can get is, like with a small, slow moving river, it's only going to be able to carry smaller sizes of particles. So if you find a whole bunch of smaller sized particles together, it tells us that the environment must have been a slower moving river to be able to deposit those particles all together. If you think about the slowest moving environment that we might get, it would be a lake. And in a lake, you're going to get very fine particle settling. But now imagine what would happen if you had a very fast-moving river that suddenly opens up into a lake. What you would end up with is dropping all of the particle sizes, and they would all be mixed together. So you'd see big particles and little particles all mixed together, and that's something that will show up in one of our rock samples. See if you can find it. Finally, metamorphic rocks. The key to metamorphic rocks is understanding that they are rocks that have gone through a change based upon heat and pressure. So when you think about continent-continent collisions, well, that's going to be providing an awful lot of pressure on those rocks, causing them to change their crystal structure and reform into something different. And what we would like you to do is, as you look at the different samples of metamorphic rock, I'd like you to be thinking about, does this rock sample have similarities to other non-metamorphic rocks? Because what we find is often they will resemble the rock that they were before they went through metamorphosis. So what we're going to ask you to do in your research is to look into how did each of those types of metamorphic rocks form, what conditions did it form under, and what did it used to be? What was this rock before it went through metamorphosis? So now what your job is going to be is to go back and look at the rock samples that we have in the classroom. You're going to take careful notes on what do they look like. Be careful to not just focus on color. There's a tendency for students to sometimes overemphasize color, but you want to take note of the fact that there can be a wide variety of color variations. Take a look at what are the distinguishing characteristics that make that rock stand out so that you'll be able to identify it and keep it separate from any of the other samples that we look at. And after you have had a chance to take notes on each of the rocks, what I'd like you to do is quiz yourself. Partner up with somebody and quiz them and see if you can get to a point where you're able to identify the rock successfully. Once you've done that and you feel like you have a pretty good handle on it, I would like you to do the research to find out, you can use the computers and find out how did each of these rocks form in the past. And that's what we will discuss in the next class. Good luck. Have fun.